this lecture we'll find out the area of the green triangle. In the drawing we have a quarter circle. AOB is a quarter circle. Inside the quarter circle we have line segment PQ that is equal to 3 units. Line segment AQ equals to 5 units, and this angle APB equals to 90 degrees. Our mission is to find out the area of this green right triangle AQO. So first of all, we'll focus on the right triangle APQ. Again, we'll focus on the right yellow triangle AQO. And we'll implement this right yellow triangle AQO, the Pythagoras theorem. Here by PT is a version from Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse in the right yellow triangle APQ is AQ, therefore the square of the hypotenuse is AQ squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to PQ squared plus AP squared. I repeat again, in the right yellow triangle APQ, according to the Pythagoras theorem, AQ square equals to PQ square plus AP square. So AQ is 5, therefore AQ square is 5 square, that is 25. And it is equal to PQ square. PQ is 3, therefore PQ square is 3 square, that is 9, plus AP square. AP is unknown, so we leave it as it is. So in conclusion, we found out that 25 equals to 9 plus AP square. Here we will subtract 9 from this equation, and we get that 25 minus 9 is 16, equals to AP square. Here we will take a root out of this equation, and finally we get that AP equals to the square root of 16, that is 4. AP equals to 4 units. Here we can write down that this line segment PA or AP equals to 4 units in its length. Okay, so here AOB is a quarter circle, and we can easily complete the quarter circle to a circle, and then point O will be the center of the circle. Again, point O will be the center of the circle. So we have rule number 2 that states that a perpendicular from the center of the circle towards any chord bisect the chord. Repeat again. On rule number 2, according to rule number 2, a perpendicular from the center of the circle towards any chord bisect the chord. Here point O is the center of the circle. From the center of the circle, point O, we will draw a perpendicular on chord BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord BC as M. According to this rule, rule number 2, the perpendicular OM bisect chord BC. That is to say, OM divides chord BC into 2 halves. the first half is Vm, the second half is MC. And of course, they're equal to each other, that is to say Vm equals to MC. So we actually can implement rule number 2 in our drawing. From the center of the circle, that is to say from point O, we will draw perpendicular on AP. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and AP as M. And according to rule number 2, the perpendicular OM bisect chord PA. And because of the fact that PA equals to 4 and the perpendicular OM divides this into 2 halves, the first half PM will be equal to 2 units and the second half MA will be also equal to 2 units in its length. In the next step, we'll define the intersection point between chord AM and line segment AQ as N. We define this angle as theta. So if we focus on the right yellow triangle AMN, this right yellow triangle, in this right yellow triangle AMN, we have this angle that is equal to theta. This angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, if we focus on the right big yellow triangle APQ, the right yellow triangle APQ, we have this angle that is equal to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we'll prove that the right small yellow triangle AMN is similar to the right big triangle APQ. So I write it down. The big right triangle APQ is similar to the small right triangle AMN. So why the two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle APQ in the big triangle is equal to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. I repeat again. Angle APQ equals to angle AMN. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta, is a common angle that belongs to both triangles. It is very easy to see that angle theta belongs to the small triangle AMN, and angle theta also belongs to the big triangle APQ. So we write down that angle theta equals to itself. And we'll call to angle theta two different names. Angle theta belongs to the big triangle APQ, therefore angle theta will be called angle PAQ. And it is equal to angle theta itself. Angle theta also belongs to the small triangle AMN. Therefore, we'll call to angle theta angle MAN. Again, it is a common angle that belongs to both triangles. Repeat again. We call to angle theta two different names. Angle theta is angle PAQ, when we relate to angle theta as belongs to the big triangle and is equal to angle theta itself. That is angle MAN. When we relate to angle theta as belongs to the small triangle, or both angle theta, it is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle PQA is equal to angle in the big triangle equals to angle ANN, this angle in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. I repeat again. Angle PQA in the big triangle equals to angle ANM in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually succeeded to prove that all the three angles in the big triangle are correspondingly equal to all the three angles in the small triangle. Therefore, the two triangles are similar to each other according to angle similarity rule. So the big triangle APQ is similar, this is the sign of similar, to the small triangle AMN, according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then actually proves that the two triangles are similar to each other according to angle similarity rule. And from the fact that the two yellow triangles are similar to each other, we will conclude that the following relationship exists between their sides. That PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the big triangle over NA in the small triangle. So I write it down. PA over MA equals to PQ over MN, and it is also equal to QA over NA. Repeat again. PA over MA equals to PQ over MN equals to QA over NA. PA is 4 over MA is 2, and it is equal to PQ. PQ is 3 over MN is unknown, so we leave it as it is, and it is equal to QA is 5 according to what is given as the question, over NA is unknown, so we leave it as it is. In conclusion, we found out that 4 over 2 equals to 3 over MN equals to 5 over NA. From this equation we will derive that 4 over 2 equals to 3 over mn. So I write it down. 4 over 2 equals to 3 over mn. 4 over 2 is 2, and 2 equals to 3 over mn. Here we multiply this equation by mn, and we'll get that 2 times mn equals to 3. We'll divide this equation by 2, and finally we'll get that mn equals to 3 over 2. 3 over 2 is 1.5. So in conclusion, we found out that the length of line segment mn is 1.5 units. So I write it down in the drawing. Here, line segment mn equals to 1.5 units in its length. From the same equation, this equation will conclude that 4 over 2 equals to 5 over na. So I write it down. Four over 2 equals to 5 over na. 4 over 2 is 2, so 2 equals to 5 over na. We will multiply this equation by na, and we'll get that 2 times na equals to 5. We divide this equation by 2, and finally we'll get that na equals to 5 over 2. 5 over 2 is 2.5. So the length of line segment na is 2.5, so I write it down in the drawing. That line segment na equals to 2.5 units in its length. This line segment na equals to 2.5 units in its length. What is the length of qn? From the drawing, it is very easy to see that qn equals to qa minus na. Again, qn equals to qa minus na. So I write it down. qn equals to qa minus na. Again, qn equals to qa minus na. So qn equals to qa is 5, and we just right now found out that na equals to 2.5, so qn equals to 5 minus 2.5, that is 2.5. So qn equals to 2.5 units in its length, so I write it down in the drawing that qn equals to 2.5 units. qn, this line segment qn equals to 2.5 units in its length. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle, therefore we will block the right ring triangle AQO by a circle. So I will copy the right ring triangle AQO in a new page, and we will block it by a circle. So actually, this is the right ring triangle AQO that I copied from the original drawing. Now we'll block this triangle by a circle. So inside this circle, we have peripheral angle AOQ that is equal to 90 degrees. So I will write it down. Peripheral angle AOQ, this angle, equals to 90 degrees inside. And we have rule number 5 that says that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. So, repeat on rule number 5 again. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Peripheral angle ABC, this peripheral angle equals to 90 degrees, therefore this peripheral angle rests on the diameter of the circle. AC is the diameter of the circle. So you can see that the peripheral angle that is equal to 90 degrees rests on the diameter of the circle, that is AC. We can implement rule number 5 in our drawing. Because of the fact that peripheral angle AOQ rests equals to 90 degrees, therefore it rests on the diameter of the circle. That is to say, AQ is the diameter of the circle. So I will write it down. Chord AQ is the diameter of the circle according to rule number 5. We know that the diameter of any circle equals to 2 times the radius. That is to say, the diameter of this circle equals to 2 times r from one side, but from the other side, it is given us the equation that AQ equals to 5 units in its length. And from this equation, we derive that 5 equals to 2r, 5 equals to 2r. We divide this equation by 2, and finally we get that r equals to 5 over 2 is 2.5. R equals to 2.5 units in its length. The radius of this circle is 2.5 units. In the next step, I will copy this point N in our drawing here. This is triangle AOQ. This is also the same triangle AOQ. So we copy this point N exactly to this triangle AON. It will be located at the same location as point N here is located along side AQ. This is point N that I call it from the original drawing. Again, this is point N that I copied from the original drawing. Line segment AN equals to 2.5 units in its length. And line segment NQ, it is also equal to 2.5 units in its length. repeat again, line segment AN equals to 2.5 units in its length, and line segment NQ equals also to 2.5 units in its length. The radius of this circle equals to 2.5 units, and AN also equals to 2.5 units. Therefore, AN must be the radius of the circle. Why? Because it's located on the diameter QA. Likewise, NQ equals to 2.5 units in its length, and the radius of the circle also equals to 2.5 units, and because of the fact that QN is located on the diameter QA, NQ must be also the radius of the circle. Where is the center of this circle? Actually, the center of any circle is located at a point where the diameter is bisected into two halves. The diameter is QA, that is equal to 5 units. 5 over 2 is 2.5. So at point N, the diameter QA that is equal to 5 units is bisected into two halves. The first half is AN that is equal to 2.5, and the second half is NQ that is also equal to 2.5 units. Therefore, point N is the center of the circle. Point N is the center of the circle. Another reason that point N is the center of the circle is because of the fact that at point the center of any circle is at a point where the two radii touch each other. At point N, the two radii touch each other. The radius QN ends at point N, and the radius AN also ends at point N. That is to say, at point N, the two radii touch each other. Therefore, point N is the center of the circle. Anyway, point N is the center of the circle for two reasons. In the next step, we join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is the point of the circle itself. This is exactly the definition of a radius. Therefore, NO is the radius of the circle that is equal to 2.5 units. So I write it down here that NO is the radius of the circle that is equal to 2.5 units. In the next step, we'll implement the Pythagoras theorem on the right triangle AMO. So I copy the right triangle AMO in a new page and implement on it the Pythagoras theorem. Side AM equals to 2 units in its length. what is the length of side MO? From the drawing it is very easy to see that MO equals to MN plus NO. Again, MO equals to MN plus NO. MN is 1.5, NO is 2.5, therefore in total MO equals to 1.5 plus 2.5, that is 4. So this is the right triangle AMO that I got from the original drawing. By PT is the version for Pythagoras theorem. So according to the Pythagoras theorem, the square of the hypotenuse is AO squared equals to the sum of the squares of the perpendiculars. It is equal to AM squared plus MO squared. So AO squared equals to AM squared. AM is 2, so AM squared is 2 squared, that is 4, plus MO squared. MO is 4, therefore MO squared is 4 squared, that is 16. In conclusion, found out that AO squared equals to 4 plus 16, that is 20. We'll take out of this equation, and you get that AO equals to the square root of 20 units. So I write it down in the drawing. That AO equals to the square root of 20 units. AO equals to the square root of 20 units. In the next step, I'll copy the right great triangle AOQ in the new page, and we implement on this right great triangle AOQ the Pythagoras theorem. The hypotenuse AQ equals to 5 units and AO equals to square root of 20 units. So actually this is the right great triangle AOQ that I copied on the original drawing. By PT is a version for Pythagoras theorem. According to the Pythagoras theorem, we get that AQ squared equals to AO squared plus QO squared. So AQ is 5, therefore AQ squared is 5 squared, that is 25, and it is equal to AO squared. AO is square root of 20, therefore AO squared is square root of 20 squared, that is 20, plus QO squared. Here we subtract 20 from this equation, and you get that 25 minus 20 is 5, is equal to QO squared. Here we take out of this equation, and finally we get that QO equals to the square root of 5 units. So I write it down in the drawing. QO equals to the square root of 5 units. Now it is very easy to find out the area of the green right triangle AOQ. So the area of the green triangle AOQ square brackets is the same for the area. Since the area of triangle AOQ equals to the area of any triangle equals to the base of the triangle times the height to the base over 2. The height must create 90 degrees with the base. So the height of the green right triangle AOQ is QO. The base of the right green triangle AOQ is QO, and the height is AO. Why the height is AO? Because it creates 90 degrees with the base QO. This angle equals to 90 degrees. Again, the base is QO, the height is AO over 2. QO equals to the square root of 5 units. AO equals to the square root of 20 units, all divided by 2. Again, QO equals to the square root of 5 units, AO equals to the square root of 20 units over 2. We have the algebraic identity that states that the square root of A times square root of B equals to the square root of A times B. We'll use this trigonometric identity here. The square root of, according to this trigonometric identity, we'll get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 divided by 2. 5 times 20 is 100, so inside the root we have 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So if I know that the area of the green right triangle AOQ equals to 5 square units. We'll repeat again, the area of this green right triangle AOQ equals to 5 square units. In the next step, I'll summarize the lecture. So, in this lecture we found out the area of the green right triangle AOQ. It is given us the question that line segment PQ equals to 4 units in its length, line segment AQ equals to 5 units, and this angle APQ equals to 90 degrees. Our mission is to find out the area of the green right triangle AOQ. So, we focused on the yellow triangle APQ, and we implemented in this yellow triangle APQ the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The hypotenuse in the right yellow triangle is AQ, therefore the square of the hypotenuse is AQ squared. It must be equal to PQ squared plus PA squared. Repeat again, in the right yellow triangle APQ, according to the Pythagoras theorem, AQ squared equals to PQ squared plus AP squared. AQ equals to 5, therefore AQ squared is 5 squared, that is 25. PQ equals to 3, therefore PQ squared is 3 squared, that is 9, plus AP squared. We subtract the 9 from this equation and found out that 25 minus 9 is 16 equals to AP squared. We took out of this equation and finally we found out that AP equals to the square root of 16, that is 4. So here, line segment PA or AP equals to 4 units in its length. So, AOB is a quarter circle, and we can easily complete the quarter circle to a circle, and then point O will be the center of the circle. And we have rule number 2 that says that whenever you draw a perpendicular from the center of the circle, that is to say from point O towards any chord, it will bisect the chord. Repeat again on rule number 2. According to rule number 2, a perpendicular from the center of a circle towards any chord bisect the chord. Point O is the center of the circle. For point O, we draw perpendicular towards chord BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We find the touching point of the perpendicular from point O and called BCSM. So according to this rule number 2, the perpendicular OM bisects chord BC. That is to say, divide this into two halves. The first half is BM and the second half is MC. And the force BM equals to MC. Okay, so you can implement the rule number 2 in our drawing. Now because in our drawing, from the center of this circle, that is to say from point O, we draw perpendicular on chord PA. So this angle equals 90 degrees and this angle equals 90 degrees according to our construction. If you find the touching point of the perpendicular from point O and PA SM, according to number 2, the perpendicular OM bisects chord PA. That is to say, divide this into two halves. And because of the fact that PA equals to 4 units, it means that the first half will be equal to 2 units and the second half MA will be also equal to 2 units. Okay, then we define the intersection point between chord AM, the perpendicular OM and line segment QASN. Then we define this angle as theta, and if we focus on the right angle triangle AMN, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, if we focus on the right big yellow triangle APQ, in this right yellow triangle, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we prove that the small right yellow triangle AMN is similar to the right big yellow triangle APQ. Okay, so why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle APQ equals to angle in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, we have angle theta is a common angle that belongs to both triangles. So angle theta equals to itself. We call to angle theta two different names. Angle theta is angle PQA and it equals to itself. Angle theta it is also can be called as angle ANN. Angle theta is angle PAQ in the big triangle and is equal to angle theta itself, that is angle MAN. If we look at angle theta, it belongs to the small triangle. Okay, it is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So here, angle PQA in the big triangle equals to angle MNA in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we succeeded to prove that all three angles in the big triangle are correspondingly equal to all the three angles in the small triangle. Therefore, the two triangles are similar to each other according to angle similarity rule. So the big triangle APQ is similar, this is the sign of similar, to the small triangle AMN according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you actually proved that the two triangles are similar to each other according to angle similarity rule. From the fact that the two triangles are similar to each other, we will conclude that the following relationship exists between their sides. That PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it's equal to QA in the big triangle over NA in the small triangle. I'll repeat again. PA over MA equals to PQ over MN equals to QA over AN. PA is 4, MA is 2, PQ is 3 over MN. QA is 5 and AN is unknown. So in conclusion, we found out that 4 over 2 equals to 4 over MN equals to 5 over NA. From this equation, we derive that 4 over 2 equals to 3 over MN here. 4 over 2 is 2, so 2 equals to 3 over MN. We multiply this equation by MN, and finally we found out that 2 times MN equals to 3. We divided this equation by 2 and we found out that MN equals to 3 over 2, that is 1.5. So this line segment MN equals to 1.5 in its length. From the same equation, we derive that 4 over 2 equals to 5 over AN, or NA. So here, 4 over 2 equals to 5 over NA. 4 over 2 is 2, so 2 equals to 5 over NA. We multiply this equation by NA and we found out that 2 times NA equals to 5. We divided this equation by 2 and finally we found out that NA equals to 5 over 2. 5 over 2 is 2.5. So here, line segment NA equals to 2.5 units in its length. What is the length of line segment QN? Or line segment QN equals to QA minus NA. Again, QN equals to QA minus NA. Repeat again, QN equals to QA minus NA. So QN equals to QA, that is 5, minus NA, NA is 2.5. In conclusion, QN equals to 5 minus 2.5, that is 2.5. So QN equals to 2.5 units in its length. Then we know that every triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. So we blocked the right hand triangle A or Q by a circle. So I copied the right triangle A or Q in a new page and we blocked it by a circle. So here, this is the right triangle A or Q that I copied from the original drawing. And we blocked it by this circle. In this circle, we have peripheral angle A or Q, this angle that is equal to 90 degrees. So, and we have rule number 5 that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. Repeat again on rule number 5. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here, peripheral angle ABC equals to 90 degrees, therefore it rests on the diameter AC. AC is the diameter. So we can implement rule number 5 in our drawing. Because of the fact that peripheral angle A or Q equals to 90 degrees, it rests on the diameter of the circle. That is to say, AQ is the diameter of the circle. AQ is the diameter. We know that AQ equals to 5 units. It is given as the equation from one side, but the diameter of any circle is 2 times the radius. It is 2r. From this equation, we derive that 5 equals to 2r. 5 equals to 2r. We divided this equation by 2, and finally we found out that the radius of this circle equals to 5 over 2, that is 2.5 units. QA is the diameter. But before that, we copied, this is the right triangle A or Q that I copied from the original drawing. This is also the right triangle A or Q. So I copied point N to the same triangle here. Okay. And AN equals to 2.5. and Q also equals to 2.5. And because of the fact that AQ is the diameter of the circle, and AN equals to 2.5, but the radius of the circle also equals to 2.5 units. Therefore, AN must be the radius of this circle. AN is the radius. Likewise, NQ equals to 2.5 and the radius also equals to 2.5. And because of the fact that NQ is located on the diameter AQ, NQ must be the radius of the circle that is equal to 2.5 units. What is the center of this? Where is the center of this circle? Actually, we have the rule that in any circle, The center of any circle is located at a point where the 2 and the eye, the center of any circle is located at a point where the 2 and the eye touch each other. Here we have the radius AN, it ends at point N. We have the radius QN that it ends at point N also. Therefore point N is the touching point between the 2 radii, and therefore point N is the center of the circle. And we have also the rule that the center of any circle is located at a point where the diameter is bisected into 2 halves. The diameter is AQ and it is equal to 5 units. 5 over 2 is 2.5, and the first half of this diameter is AN, and the second half, that is equal to 2.5 of course, and the second half is NQ, that is also equals to 2.5. That is to say, at point N, this diameter AQ that is equal to 5 units, it is bisected into 2 halves. Therefore, point N is the center of this circle. So we have 2 reasons why point N is the center of this circle. So point N is the center of the circle. We join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is a point on the circle itself. Therefore, NO is the radius of the circle, that is equal to 2.5 units. Here, line segment NO is the radius of the circle, that is equal to 2.5 units. In the next step, we implemented the Pythagoras theorem on the right triangle AMO. So according to the right triangle AMO, in the equation we implemented here the Pythagoras theorem. AM equals to 2 units, MO equals to MN plus NO. MN equals to 1.5, and O equals to 2.5, so in total MO equals to 1.5 plus 2.5, that is 4. Here, MA equals to 2, MO equals to 4. So this is the right triangle MO that I copied from the original drawing. According to the Pythagoras theorem, AO square equals to AM square plus MN square. AO square equals to AM square. AM is 2, so AM square is 2 square, that is 4, plus MO square. MO is 4, therefore MO square is 4 square, that is 16. So if we're going to find out that AO square equals to 4 plus 16, that is 20. We took out of this equation, we found out finally that AO equals to the square root of 20 units. AO equals to the square root of 20 units. In the next step, I will copy this right triangle, AQO in the new page, and we implemented in this right green triangle the Pythagoras theorem. The hypotenuse AQ is 5, and the side AO equals to square root of 20 units. This is the right triangle AQO that I copied from the original drawing. According to the Pythagoras theorem, AQ square equals to AO square plus QO square. AQ is 5, therefore AQ square is 5 square, that is 25, and it is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 square, that is 20, plus QO square. We subtracted 20 from this equation, and finally we found out that 25 minus 20 is 5, so 5 equals to QO square. We took out of this equation and found out that QO equals to the square root of 5 units. Here QO is square root of 5 units. Now it is very easy to find out the area of this green right triangle AQO. The area of the green triangle AQO equals to the base of the triangle times the height over 2. The base is QO, the height is AO, because it creates 90 degrees with the base over 2. QO is square root of 5, AO is square root of 20 divided by 2. We have the algebraic identity that says that square root of A times square root of B is square root of AB, therefore square root of 5 times square root of 20 is square root of 5 times 20 over 2. 5 times 20 is 100. So inside the root we have 100 over 2. The square root of 100 is 10, so 10 over 2 is 5. In conclusion, we found out that the area of this green right triangle AQO is equal to 5 units. 5 square units. Repeat again, the area of this right triangle AQO equals to 5 square units. Okay, thank you very much.